Good afternoon, everyone. We still have 2 minutes before we start, but just so we can keep everything on time, I'd like to just start with a few housekeeping details. So we have 6 presentations today, and that means around 20 minutes per person. But there's always, things and you have to switch presentations, so it's a little bit of troubleshooting. So I want to ask the presenters to finish your presentation within 14 minutes. And then so we can have for each presentation 5 minutes of questions and answers. So again, 14 minutes presentation and then 5 minutes of questions and answers. And the remaining 6 minutes we're probably gonna use probably in troubleshooting or something like that. So is the first presenter Yui Sao present?
Hello, yes, I'm here.
Okay, great. So if possible, I will ask you to turn the video on when you're presenting. And whenever you're ready, you can share your screen.
Yeah, I will share my screen now. Um, uh, I need to quit and reopen Zoom again to share.
Okay, can we move on to the next presenter then? You can be the second one.
Okay,
Because
sure, of
okay.
course.
So it's I'm gonna murder this name. Shohan Liu present.
Uh, okay, let me see.
Is it okay if you can present first?
It's okay.
Okay, thank you.
How do I wait one minute?
No problem.
Screen. Yeah.
You
I
see,
don't
that extra minute is for that.
I don't know if you can mind. Yeah, this one,
This
right?
one, yeah.
Okay.
Share.
Yeah, I think we're gonna share. Can you put to this? Yeah.
Uh, okay, can you see my screen?
Yes.
Okay, hi everyone. I'm Xiaohan, and we're presenting today our paper, Synthesizing Travel Demand in Data-Scarce Cities, a case study in Phnom Penh, Cambodia. Okay, let me see. Rapid urbanization and motorization in developing countries, particularly in Southeast Asia, have created an urgent need for better transportation planning. And cities are now experiencing rapid growth, but often lack the data and the technical capacity to support a comprehensive understanding of mobility. So in the field of travel demand modeling, there are a widespread difference in modeling practice between countries. While some cities have advanced simulation tools, many others face significant gaps due to data scarcity and high implementation barriers. This highlights a clear need for scalable and data-efficient methods tailored for those developing urban environments. So in the field of travel demand modeling, there are two major approaches commonly used: activity-based models and trip-based models. Well, activity-based models offer detailed behavioral insights. They require extensive data like household travel surveys, detailed land use maps, and POI data, which are often unavailable or unreliable in data-scarce cities. Trip-based models are simpler but might be more suitable in those contexts due to their lower data requirements and implementation demands. So our study addressed this gap by proposing a lightweight generative modeling approach that builds on small sample GPS data to synthesize large-scale travel demand. Unlike traditional method that depends on extensive surveys, our approach leverage the increasing of availability of mobility data, such as GPS data, to generate meaningful insights with minimal input. The method is designed to be technically sound but practical, with the focus on scalability, accessibility, and low computational burden. Ultimately, we aim to support data-driven transport planning in cities where conventional modeling remains out of reach, enabling broader adoption of mobility analysis in the global south. So our research focused on Phnom Penh. Phnom Penh is a rapidly growing city facing problems brought by rising mobility demand. As the population expands and private vehicle ownership accelerates, the city struggles with congestion, limited public transport, and a lack of reliable data for planning. Conventional travel demand models are often impractical due to data and resource limitations. So this is the overview of our method building on kernel density estimation, or KDE. The goal is to generate trips that replicate both the temporal and spatial patterns of actual GPS tracked trips. As shown in the flowchart, our method includes 3 key steps. First, we identify trips from raw GPS traces. Second, we use k-means clustering to split the dataset into smaller subsets. And third, we apply KDE on each subset to generate synthetic trip data that reflects the original patterns. In our case in Phnom Penh, we adopted a rule-based approach to identify trips, and the method is shown in the red chart. So from the GPS data, we are able to identify around 44,000 trips, each trips with the start time or OD pairs, OD coordinates, and those becomes the input of our generative model. Before we start to generate trips, we analyzed the key temporal and spatial patterns in the original dataset that we need to ensure they were accurately reflected in the output. So first, the city exhibits a monocentric structure with a high concentration of trip OD in the urban core, and that gradually decreased to the periphery. Temporally, we observed the 2 clear peak period, the morning peak hour and evening peak hour. And the last one is the trip distance distribution, shows a long tail distribution with most of the trips being short and a few extending to a longer range. So the trip distance is not the variable we want to generate, because once we generate the OD, we will have the distance along their road network. So after we generate those trips, we can calculate the network distance as one of our methods to verify whether our method can replicate these distribution patterns. One of the challenge with KDE is that it tends to smooth out sharp patterns in the data. So in our case, this means it will over smoothing the distinct 2 peak temporal patterns, the morning peak hour and evening peak hour, which is one of very important pattern of the city scale travel pattern. So this will be even more important if we want to generate a travel demand for a longer period, because there will be even more peaks during a longer time. So to preserve this structure, we use k-means clustering to segment the dataset based on trip start time. After testing different cluster numbers, we found out in our case, dividing the dataset into 2 subsets effectively preserve the underlying patterns while simplifying the model in our case. So with the data subsets, we then apply KDE to generate synthetic trips for each subset. Each KDE model is trained on the subset's key variables, start and end coordinates, and trip start time. We use Silverman's rule of thumb for band 1 selection, which simplifies implementation and avoid high computational cost. Importantly, the number of synthetic trips generated per cluster is proportional to the original subset size, preserving the overall distribution. To ensure realism, every generated point that falls outside of Phnom Penh or falls into inaccessible areas like water bodies are removed. So the model will continue generating points until a valid synthetic dataset is achieved. So using our method, we are able to generate a total of 8 million synthetic trips from Phnom Penh. This is based on the number is based on GPS data showing that Phnom Penh residents take an average of 3 trips per day, scaled to the city's 2.6 million population. To verify the scales, we use QQ plots, which shows strong alignments between the generated and original data across all variables. The spatial distribution of ODs also matched well, preserving the city's monocentric structure. And although the trip distance is not directly generated, but we derive them from the OD pairs, and we can see the distribution also follows the similar patterns of the original dataset. So all those validations demonstrate that our method reliably captures those travel patterns in Phnom Penh, able to support its use in urban transport planning. So in summary, we proposed a lightweight and scalable method for synthesizing travel demand in data-scarce cities. Our approach combined KDE and K-means clustering to balance simplicity and effectiveness. We generated 8 million synthetic trips from a small GPS sample. It's designed for practical use with low technical barriers and enable data-driven traffic simulations in cities lacking traditional data like household travel service kind of data. A key limitation of our method is that currently we do not handle transport modes, as there is a huge variety of transport modes in Phnom Penh, like tuk-tuk, motorcycle, bicycle, walking, and other transport modes. So in future work, a more specific models can be trained, and this approach can be adopted to larger or more complex urban areas. So this work was supported by Singapore University of Technology and Design, and we are from LKY Lee Kuan Yew Center of Innovative Centers. If you're interested in our other works and future works, you can take a look at our website. Thank you for listening.
Thank you very much. And we have 10 minutes for questions, so we can talk a lot. So are there any questions? If you have any questions, you can please post them on the chat. But one from me, can you show the slide showing the quantile plots?
Oh, wait, one sec. This one?
I'm seeing the cover present. Yeah, that one, yes. So what you were able to synthesize is the distribution, right? So essentially origins and destinations. Is that correct?
Yeah, yeah.
So like but what about, for example, other things like purpose, right? Inferring travel purpose, I think is very important for transportation planning. So are there any ways that you can think about maybe time periods, or I don't know what kind of sociodemographics you have on this GPS data, but is there any information about that, or trip chains, for example?
Actually, all we have is only the GPS data, and the data is anonymous, so we don't have any social demographic
Okay.
features of all those users or what is their travel purpose. And also, one of the reasons we adopt this method is actually a trip-based approach.
Yeah.
It doesn't consider activity chains or activity purpose. One of the reasons is because we found out all those data can be used to infer the travel purpose are not very reliable, or they are not available, or even we can find some data, they are not very reliable, they are not updated. And also we found out during our field trip, we found out there is a high level of informal practice in the
Yes,
cities. So in most of the developed cities, they are able to infer their travel purpose by where they go, by linking them with POI or with land use, but we are unable to because people go to very random place for very random purpose. For example, there are street vendors. We can find out they go to the middle of the street only at noon, but they buy food for street vendors, but the street vendors were not on POI data, or they will disappear after 1 hour. So this kind of informal practice made it very hard to identify their travel purpose. Even we want to, the accuracy is highly doubted. So this is also why we think trip-based method might be better in those data-scarce cities, because from the city scale, their behavior really looks very random.
Okay.
Yeah.
I see. And how long is the observation period for this? You have 10,000 residents, right? Is it one day? What is that?
This dataset is from 1 week.
Well, and you know, it's not the IDs are consistent across days. So the same ID
Yeah.
for the whole week.
Yeah. Same ID for a whole week.
Okay, because I would assume that, of course, maybe those kind of rare or kind of unexplainable patterns exist, but there probably might be another type of patterns that you can probably capture by observing the whole week, right? So if you see that, for example, the same repeated pattern of, I don't know, nine to five on weekdays, you can assume safely that that's probably a work trip, right? So I do not know the quality of the data, but it seems that it's possible to extract at least the most basic trip purposes with your analysis.
Yeah, we agree with that. I think this is one of the future direction we can try to infer more information based on their behavior.
Okay. Okay, I still have 6 minutes. Any other questions regarding this presentation? Please post them in the chat. Okay, so while people think, another thing, it's mostly an information sharing, but JICA, so the Japanese International Cooperation Agency, they did a household travel survey in Phnom Penh.
Yeah, we
I
see.
think a couple of years ago.
But their data are confidential. They won't share with us.
Did you ask?
No, they won't share the data with us.
Okay,
We did read their report.
okay, because I know also like maybe because this one is too recent, but like the archive of a lot of household travel surveys in Japan, that Japan conducted, JICA conducted in Southeast Asia are in the Center of Information Special Science of the University of Tokyo. So part of the data is openly available, it's publicly available.
Okay.
So I don't know if the most recent one, the 2023 is, but some old data might be there. So might be a good validation data set for you guys.
Okay, thank you so much for the information. We will try to see that.
Okay.
Yeah, thank you.
Okay, so I don't see anything else in the chat, so maybe I will wrap it up here, unless no. Okay, let's wrap it up here. Thank you very much. Now I would like to move to the first presenter. Are we ready? Misao. Yes. Oh wait. Andresa, can you make Rebecca Z a co-host so she can share her slide and open her mic?
Yeah, sure.
Okay.
All right. Okay. I got
Great.
it. Wait, let me try to open the video.
Yeah, we can see it. Perfect.
Okay, great. All right. Let me share my screen.
Oh, yes, we can see it. Great.
All right, great.
Let's do it.
Should I start?
Yes.
All right. Good afternoon, everyone from Sydney, Australia. I'm Rebecca, or you can call me Ray. Today, I'm sharing the research on progressive subsidy allocation for transport equity and efficiency. It was conducted by me with my supervisors, Dr. Taha and Dr. Travis. So I will structure my presentation in these three main parts. First, I will provide some of the background of my research, why this matters, and then I'll explain our ABM-ETOP framework and how it works. And finally, I'll share our key findings and policy recommendations. And then we'll have some time for the questions at the end. So here's a striking fact that there are 57% of Australians drive to work, but only 4.6% use public transport. Now, look at families without cars, often elderly people, single mothers, or low-income families, not by choice, but because they have no other option. And this is what we call the transport poverty. Your income determines whether you can get to a job interview, reach a hospital, or visit family. It's not just unfair, it traps people in disadvantage. And here is a closer look at those zero-car households in outer Melbourne. walking dominates at 54% of their trips, with other limited modes making up the rest. These households face longer travel times, fewer travel options, and higher costs relative to their income. This isn't just inconvenient, it's a barrier to social and economic participation that perpetuates the inequality. And this brings us to our central research question. Despite the major public spending on transport services worldwide, transport inequality continues to persist. Are our current policies actually effective at addressing these problems? And this question motivated us to develop a better way to design and evaluate transport subsidy policies. And the solution would be the ABM-ETOP framework that we develop, and it is short for the agent-based model for equity transport optimization and policy. This is a purpose-built system designed specifically to evaluate and optimize transport policies with equity as a primary consideration rather than an afterthought. Let me explain how our ABM-ETOP framework works. This is the architecture. The framework operates through 4 integrated layers. The agent layer simulates individual commuters, transport providers, and a coordination system. And then next is the policy intervention layer. It implements our 2 main subsidy mechanisms. First is the fixed pool subsidy, and second is the percentage-based subsidies, which I'll explain in details shortly. The system outcomes layer measures 3 key metrics. First is the mode share equity, and then travel equity, and then total system travel time. Finally, the optimization layer uses Bayesian processes to continuously improve policy parameters based on performance feedback. This creates a feedback loop where we can test different subsidy configurations, see how they affect individual travel decisions, and measure the system worldwide outcomes, then optimize for better results. The core of our agent-based model is the 3 agents. The commuter agents, you can think of it as our real people that's traveling in real life with different income levels, ages, and travel needs. They make travel decisions based on the cost, their time, and personal preferences. And then the provider agents represent the companies such as the public transport, buses and trains, and then the ride-sharing companies such as Uber, and then also bike sharing, each with their own capacity constraints and pricing. Lastly is what I call it the mass agent. It acts as an intermediary people. It works like a smart transport app that coordinates between the commuter's needs and the availability of the providers. And then it also apply the subsidy policy into it. And here's how these agents interact in practice. The commuters, they book the trips through the mass agents with communication of pricing, availability, and booking informations with the transport providers. After they successfully book a trip, the commuter is gonna go for a trip, and this mirrors how many people, and then after successful booking, the commuters will make that information available to the mass agent, and this mirrors how many people already use transport apps, but with intelligent subsidy allocation that has been assigned using the mass agent that has been built into it. I won't dive deep into the technical details, but here is just a briefly screenshot shows the sophistication behind the system. We built the comprehensive database tracking all transport services in real time while the simulation is running. And then we implemented advanced routing algorithms such as basic algorithms as Dijkstra and A-star for the car share and bike share transport, and then Raptor for the public transit with successful transfers in between, such as which station to get on and which station to get off. And then next is the core equations, such as the utility functions, the logic model. These are the functions to decide whether or not the customer is going to take on a trip. And then we also have the BTR function to adjust the congestion of the overall network route model. So here are some baseline simulation results. We calibrated the system to match the real city patterns. The heat map to the left shows the realistic congestion. The darker the area means the higher the traffic, and congestion concentrates along major corridors naturally. And the spatial plot shows emergent behaviors. The blue dots shows the low-income commuters cluster around the public transport, and then the green dots is the high-income commuters. So when these little dots are moving, that just means all the commuters are just taking on trips, and they change into different shapes, means they took different modes of transport. And another baseline simulation result is when there is no subsidies given to any of the commuters, you can see there are large inequities where the low-income commuters average 30.9 minutes travel time compared to just 8.3 for the high-income commuters. And that is a nearly 4-to-1 ratio. And these results are from the simulations of the system. The travel time distributions show this inequity clearly, with low-income people face much longer and more variable, much longer commute time. And also some of the baseline simulation results. This is the graph showing the dynamic pricing of our car share and bike share models, and you can see how they peak during the peak hours. That is syncing with the reality. And then to the right is a dynamic mode share, as for different income levels, what mode do they take throughout the simulation. And this is the policy implications. We have built in 3 complementary metrics. The first is called the mode share equity. It basically asks, are poor people forced into certain transport modes while rich people have more choices? And then we have the travel time equity. They ask, do disadvantaged groups face longer commutes than others? And then lastly is the total system travel time. It measures the overall system efficiency by adding up everyone's travel time together. And the innovation here is optimizing for equity and efficiency, all of them simultaneously, rather than treating them as competing goals. And we are testing 2 subsidy mechanisms. First is the fixed pool subsidy, short as SPS. These are set as a predetermined total budget, like saying the government gonna pay 4,000 per day to everyone in this city, so that the government can reach some goals such as equity or efficiency for the overall travel. And this reflects real-world budget constraints and help identify optimal investment levels. And then the second is what we call a percentage-based subsidy. It essentially controls how much of the percentage are paid to different kinds of the commuters. For example, we can set the percentage that for the low-income people choosing the car share service, they're gonna get the whole trip gonna cost $50, and they're gonna get 50% of them subsidized. So this is what this percentage is controlling. And we implement this Bayesian optimization algorithm. This is how the whole algorithm looks like, but I can explain maybe a little bit in details. We can see that we are searching for 12 different parameters across 3 income groups and 4 transport modes. And it tests every combination. And this normally would take millions of simulation, but Bayesian optimization is like having a smart learning system. We start by randomly testing some allocation strategies, and then each test basically tells us when we give 40% of the subsidies to low-income bus users and 20% to high-income car share users, here's what happens to the equity and efficiency. After a few tests, the algorithm builds a statistical model, and this model says, based on what we've seen so far, if we try this new allocation, here's how well we expect it to perform. It's making educated guesses about untested combinations. And the clever part is how it picks what to test next. The algorithm balances two things, testing strategies similar to good ones and trying completely different approaches we haven't explored yet. It asks which untested allocation gives us the best chance to beating our current best results. And every test we run for 144 steps. That means just for a whole one day from 12 a.m. to the next day 12 a.m. in our simulation. And we repeat it for several iterations. So we can see up to around 8 to 9 simulations, we can see that the results stabilize, and that would be our best PBS combinations. So based on all these simulations and optimization algorithm and everything, we come to our main findings. So this is our main finding. The y-axis is the fixed pool subsidy, as in how big the budget that the government gonna pay, for example, for each day. And we can see that in our agent-based model system, a clear optimal investment range should be around $3,000 to $4,000 for our fixed pool subsidy. And when it's below this range, we see rapid improvement in all three metrics. But above this range, the returns stabilize. You don't get much additional benefit of additional spending. So that means the government maybe should not pay more than that. And most importantly, we found that equity and efficiency as the three metrics, they can be achieved simultaneously. The common assumption that you have to choose between either fairness or effectiveness, efficiency is simply wrong, because you can see how there is a point that everything just get to the best results. And another policy result is that our optimization consistently found that the best performing policies allocate the largest proportion to the subsidies to low income level groups. That's around 55 to 65%, regardless of which objectives we're optimizing it for. And this progressive distribution emerged naturally from the optimization process, not from predetermined assumptions about fairness. And then we can simply imply our simulations from our ABM-ETOP framework into, say, a medium-sized city. So we recommend that an optimal FPS value of 4,000 units, we recommend it to be equivalent of around 16 million annually for a medium-sized city. And definitely the government should allocate 55 to 65% to low-income groups and 25 to 35% to middle-income groups and 5 to 10% to high-income groups, etc. So this is just generated like simply scale up from the simulation result that we found from our ABM-ETOP framework. And since our ABM-ETOP framework is highly flexible, the government or any policymaker want to use it to have a more specific results, they can just simply put in their data into our framework and generate the results on their behalf. So that is basically all from me. And we can see that well-designed transport subsidies can advance equity and efficiency simultaneously. And this ABM-ETOP framework gives transport authorities a practical tool for evidence-based policy design. And thank you so much for listening. I would love to hear from your thoughts. And if you want, you can definitely reach out to me on LinkedIn, and we can maybe collaborate and discuss more. Thank you so much.
Thank you very much. Are there any questions for Rebecca? Okay, while they warm up. So I have a question about the premise. So you mentioned at some point the idea of mode shared equity. Can you show that slide?
This one?
Here, yeah. So you measure how equally different transport modes are used under income groups.
Yeah.
But I would assume that My first guess will be like even if you can still have a fair system, even though you have differences in the use, right? So I mean, having the option to use, for example, a car for lower incomes is not necessarily a good thing if you can guarantee that they have certain level of accessibility or a good level of accessibility with transit, right? So, what do you think about that? Like, I mean, maybe the having this mode share equity is necessarily the best interest of society as a whole.
But we more like we want to focus on somehow like equity as in because what we found is even though there is such options as when there are in emergency, for example, when the
Yes.
low income people are in emergency, they could not even take the car mode as a mode that they can go to, for example, hospital. And then we just want to make sure that everyone has the equal chance to reach different modes, and that's why this is here. And yes, that is a good question because although there are car modes available, is it even necessary for people to take it? So that is also actually taken into account as when we are generating the request, they can also so for our agents in our simulation network, they can also specify what is the purpose of this trip. And then that's going to add up to the utility function of whether or not they actually need the car mode or they need something else. And that's also just all going to be taken into considerations.
Okay, so in this definition of mode, you also, because going back to your example of an emergency, then probably, okay, you don't have to own a car, but you can use a taxi or you can use a shared service, I guess.
Yeah.
So private owned vehicles are also included into this calculation, or you're not considering that?
No, so private, we did not even consider the
Okay,
private.
okay.
It's just all sharing.
Okay, I understand. Thank
Yeah.
you. Are there any other questions? Okay, if not, then I want a clarification. So in the optimal results, where you have the plot that you said $4,000.
Here, this one.
Yeah, that one. So you have a fixed pool subsidy. Can you explain again? So what you're talking about $4,000 annually per person?
Okay, so here's what happened. I don't have enough time, so it's just a rush. So in my system, I represent the fixed pool subsidy as so this part as you can think it as how the government pay everyone in total. That's government's gonna pay 3,000 each day. And in my system, I use Sydney as my network. So say Sydney government gonna pay $3,000 each day to everyone, but the government, they can't really control like who are they paying to. So that's what we're optimizing for. So in the end, we got the optimization. We say that for that $3,000 in total, maybe 55% of them gonna pay to the low income people, and then maybe 6% or 10% need to pay to the high income people, and that's gonna give us the best results.
Okay, and then is this? Feel free to chime in. I mean, we still have 4 minutes. I'm talking to the audience. So is this for 4,000, 3,000 based on a budget constraint that the Sydney government has, or in this case, is arbitrary?
So we used different. I couldn't really remember which one of the examples that we used, but we did look at different policies from different countries, and we just choose this one as an example. And it doesn't necessarily reflect is that exact amount that Sydney government is paying. It's just within our network, we have 120 commuters, and we have 85 times 85, that a big amount of grid, and that's how much they are utilizing. So if we actually want to have like a policymaker, if they actually want to take our advice, then we need to actually build a full functioning Sydney network with actual policies, as in actual actual subsidies that government pays to the, and we didn't put that in here.
No, very interesting. But I think I would hope that probably incorporating some kind of cost constraints will like make it easier for policymakers to understand because it's like how much is it gonna cost, right?
Yeah, yeah.
Okay.
Thank you.
Thank you very much. I don't see any questions in the audience. I think they may be tired from today and yesterday and today, but let's wrap it up here. Thank you very much.
Thank you.
And then let's move on to the third presenter, which I hope is here.
I did hope he's not here.
Oh,
Yeah.
So Ming Wang is not here.
Yeah, not here.
Okay, so can we move to Atsushi Suzuki from Totoro University?
Hello.
Hi.
Can you hear my audio?
Yes, I can hear you.
Share my screen.
Yes. And if possible, also turn your video on. Okay.
Uh, can you see my slide?
I think yes. Okay, good. Go ahead.
Thank you. Hello, everyone. My name is Atsushi from Tokyo University, Japan. I will present our work of this title. We will introduce the background of this study. Connected and automated vehicle CAV strategy against freeway congestion for extremely low CAV penetration rate. Jam-Absorption driving JD is a method performed by a single CAV to clear a shock wave. JD actions are composed of throw in and pass out. JD actions may cause secondary waves categorized into 1. High density region and 2. A secondary shock wave. The solutions of these problems are 1. Shrinking and finally eliminating high density region. And 2. Suppressing a secondary shock wave by stabilizing high density region. We focus on the latter, suppressing secondary shock wave by stabilizing high density region. A candidate solution of secondary shock wave is support driving SD. As SD actions support vehicles, SVs dynamically extend their time gaps. SD dumps perturbation in a vehicle platoon. However, SD guaranteeing stability has not been applied yet to secondary shockwave problem in JAD. This study aims to suppress secondary shockwaves by SD. Our contributions are as follows. We design SD for suppressing secondary shockwaves. We analyze the effect of SD on stabilizing high-density region. We investigate the impact of SD on traffic performance indices. We confirming the need for reverting extend time gap and combining JD and SD. We define the system. We assumed a single lane freeway. The number of vehicles n equal 2000. Initial velocity V is 22 meter per second. Vehicle length D is 5 meter. JD vehicles JIJD is 800. Each vehicle's expect for leading and observing vehicles follows the vehicle in front of it according to a typical car following model IDM. At the initial time, vehicles run with initial velocity V in equilibrium. Target shock wave was caused by leading vehicle's temporal perturbation. In JD, observing vehicle IJD equal 800 slows down VE to observing velocity VA. We consider platoon P vehicles from IJD plus 1 to N minus 1. Observing vehicles perturbation propagates through platoon P. Perturbation grows into secondary shock wave without SD. We design support driving to stabilize the platoon. Each vehicle increases its time gap parameter T from 1 second to T large equal 50 seconds with the increasing rate 0.08. We design two patterns, no reversion and reversion of the extend time gap. Splits are deployed in platoon P at interval of NST. Set of splits ID NST is expressed at the equation. We define splits ID ISTM. K is the number of splits. We define supported state, STD state. In STD state, velocity is VA, time gap of splits T large equal 50 seconds, time gap of the others T equal 1 second. SD stabilizes platoon P in STD state. We analyze stability of platoon P by head-to-tail string stability. Head-to-tail gap error transfer function is H equal EG n-1 over EG IJAD plus 1. EG n-1 and EG IJAD plus 1 are Laplace transforms of gap error from equilibrium. When absolute value of H is greater than 1, gap error is amplified. When absolute value of H is smaller than or equal to 1, gap error is damped or stable. String stability is determined by the relationships between absolute value of H and frequency of gap error omega. If absolute value of H is greater than 1 for some omega, it is string unstable. If absolute value of H is smaller than or equal to 1 for any omega, it is string stable. Determine T large and NST to realize string stable state. We designed 5 scenarios. In no control scenario, either JAD or SD is not performed. In JAD only scenario, JAD is performed, SD is not performed. In JAD support scenario, both JAD and SD are performed. It uses no reversion SD action. In JAD support R scenario, both JAD and SD are performed. It uses a reversion SD action. In support only scenario, JD is not performed, SD is performed. It uses non-reversion SD action. We explain performance indices as follows. Measurement segment of each vehicle ranges from its initial position to x equal 20 kilometer. We use three performance indices. The first index is total travel time T total. The second index is total fuel consumption F total. F total is eliminated by emissions from traffic. The third index is surrogate safety measure inverse time to collision ITTC. Time to collision ITTC is time margin to collision. For example, when gap between two vehicles is 10 meter and relative velocity is 5 meter per second, TTC is 2 seconds. ITTC is total amount of inverse of TTC for entire measurement time summed over all vehicles. A low high value of ITTC denotes a low high collision risk. Let us explain the result of gain characteristics. A figure shows the relationship between absolute value of H and frequency of gap error omega of platoon P in STD state. Time gap parameter of SV's T large equal 50 seconds. When ANST is empty, platoon P is string unstable. When NST is greater than or equal to 300, platoon P is string unstable. When NST is smaller than or equal to 200, platoon P is string stable. This is numerical simulation result in no-control scenario. Space-time diagram shows that target shock wave was caused. Velocity time diagram shows the vehicle's velocity is 0 inside the shock wave. In JD only scenario, space-time diagram shows a secondary shock wave was caused by JD. The observing vehicle is indicated by the blue line. Velocity time diagram shows the vehicle's velocity is 0 inside the secondary shock wave. This is numerical simulation result of JD support scenario. SVs are indicated by red line. When NST equals 600, a single SV performed SD. This SV suppresses secondary shock wave, but the perturbation is amplified. When NST equals 200, 5 SVs performed SD. They suppress secondary shock wave, and the perturbation was not amplified. Let us explain the result of performance indices. Compared to no-control scenario, a JD-only scenario reduces all three indices. Since velocity of vehicles becomes 0 inside the target shock wave, removing the target shock wave was reduced T total. F total was reduced because removing the target shock wave also restricted unnecessary idling inside it and unnecessary acceleration when exiting it. ITTC was reduced because approaching stop vehicles was restricted. We compare JD support scenario with JD only scenario. T total in JD support scenario was greater than T total in JD only scenario because the scale of secondary shockwave was small and the SVs increased their time gaps in JD support scenario. F total in JD support scenario was smaller than F total in JD only scenario because the SVs mitigated the perturbation caused by the observing vehicle. ITTC in JD support scenario was smaller than ITTC in JD only scenario because the SVs restrict high collision risk situation. We explain the result of JD support R and support only scenario. We compare JD support R scenario with JD support scenario. T total in JD support R scenario was smaller than T total in JD support scenario because the SVs return their extend time gap. T total in JD support R scenario was greater than F total in JD support scenario because the SVs returning their extend time gap induced extra acceleration to the following vehicles. ITTC in JD support R scenario agreed with ITTC in JD support scenario because the SV's returning action did not cause high collision risk situation. Support only scenario increased all three indices compared to the other scenarios. We summarize our contributions in here. We investigate the impact of SD on the suppression of secondary shockwave in JD. Combination of JD and SD has a significant impact on preventing secondary shockwaves with an extremely low penetration rate of CAVs. Thank you for listening.
Thank you very much. Are there any questions regarding this presentation? Please post them on the chat. Okay, so I'm not sure I completely understand the details, but can you show the results when you compare the which one was it? JD with support against this one, yeah, right? So here the T is the total travel time,
Yes.
right? And what was F again?
T total in JD support scenario was greater than T total in JD only scenario.
No, I mean, what was F total? What was F total means? I forgot.
Sorry, one more please.
The meaning of F total. So
F total mean total fuel consumption.
fuel consumption. Okay. So what do you think in general? So like here the fuel consumption decrease and also the time to collision decrease, but what about the amount of increase of T total? Do you think it's something the drivers are okay, or is it an acceptable increase in total travel time?
Sorry, it is not easy for me understand your question. So
Okay. So
please a few keywords of your
okay.
question.
Wait.
Thank you. We focus on sorry, the results of reducing F total and ITTC is better than T total increase. So we think the biggest T total is biggest T total is necessary for reducing F total and ITTC for support driving.
Okay, so you think it's an acceptable trade-off?
Yes.
Okay. Okay, thank you. Are there any other questions? If there are no more questions, I would like to wrap it up here. Thank you very much.
Thank you.
And then moving on to the final presentation of today is Ms. Wang here. Can we try again sharing the screen?
Is here, dear Prof?
Okay, I'm here. Can you see it?
Yes, now it's working great.
Okay. Okay, I'm Yikun Wang, a current graduate student from the Department of Civil and Transportation Engineering, Beijing University of Civil Engineering and Architecture. Okay, let's begin. When you think of Bayesian, what comes to your mind? The subject of this presentation is effects of TIS complaints rate on parallel network flow assignment in Bayesian routing games. The background of our research is as follows. According to Data-Scarce 2025, Beijing's peak hour congestion index is 1.747. It's a big number. So what's the problem we're studying? In cases where navigation information affects traffic flow, we often assume that the complaints rate is 100%, but in reality, not everyone follows the navigation instructions. Therefore, we have incorporated the concept of complaints rate into the road game in this paper. Next, we found that the behavioral heterogeneity was overlooked from the perspective of imperfect information in previous studies. Okay, the transportation network we studied is shown in the right figure. The traffic network consists of a starting point O, an end point D, and the two parallel roads R1 and R2, which have the same origin and destination. The R1 is prone to congestion. The network has a fixed demand queue of travelers who will make decisions about choice of roads through a road choice game. Above agents is consists of two travelers groups. Each participant subscribed to one single traffic information service with TISH and TISL representing high accuracy and low accuracy TIS respectively. The groups of travelers receiving the corresponding information are inferred to as Group H and Group L, with each traveler belonging to one of these groups. Lambda H and lambda L represent the proportion of Group H and Group L. Complete optimal conditions for route selection games is that for each type of player, the expected cost of all used routes must be equal and less than the expected cost of any unused routes. Or that's Bayesian-Nash equilibrium. Okay. Therefore, the Bayesian-Nash equilibrium of game types must meet the following conditions. Look at the left picture. Two group H, two group L, two rows of expected cost must be equal. Two group H, they used in the network normal route 1, expectation cost must be strictly less than the expected cost of using route 2. Used in the route network abnormal state, route 2 expectation cost must be strictly less than the expected cost of using R1. Look at the left picture. The blue one presents the type H, and the red one represents the type L. Next, each player interim belief can be considered as a posterior distribution obtained by updating the common pair using Bayesian methods after receiving their type. The interim belief can generally be expressed. Travelers participate in the game by first subscribing to one of the two TIS with Bernoulli probability, either TISH or TISL. The stage of the game where player has received their types is known as the interim stage of the game. The Bayesian belief update formula is as follows. It is for load profile, the expected cost of group L on a given road is this. Since group L believes that the realization of this state and the type of the opponent in the game are independent, their expected value of the cost of route 1 is this. As we all know, the lambda divided our regime to regime 1 and regime 2. Wu found that the qualitative structure of the equilibrium routing strategy will be divided into two strategy cases due to the different sizes of the group H, and the boundary value of the division is this. In regime 1, group H, under the condition of the normal state, assign all of its demand to route 1. In this case of abnormal state, distributes all of its requirements to route 2. Group L will demand assigned to the two sections. In group 2, the two groups are faced with the same equilibrium of expected route cost. As a result, each group shares its demand directly on the two routes, and each route of equilibrium is the only route demand and has nothing to do with this. In regime 1, all of these conditions will switch to this formula in the right side. In the end, we take the result as a flow of root 1 like this. As same as the regime 1. Regime 2, the conditions switch to this formula in the right side. We also get the results as a flow of root 1 like this. In regime 1, the traveler selects only one route based on the navigation information. In regime 2, the traveler's route selection decisions is 2 routes, and the static game reached Nash equilibrium results. Therefore, only the complaints rate sigma of TIS needs to be considered in regime 1. The Nash equilibrium of this group of travelers with heterogeneous information in the transitional stage of the game is equal to a Bayesian workshop equilibrium of the incomplete information game, where everyone allocates their demands to the roads with minimum expected cost based on their private beliefs. The expected cost of group L for each of the 2 rows after equilibrium are the same, as shown in the following formula, like this. Numerical examples, we got it. TIS complaints route is pivotal. When sigma is higher than 50%, reduces total travel cost, especially in abnormal states. The sigma is lower than 50%, increases cost if sigma rises. Okay, look at the figure 4. Figure 4 shows the flow assignment result on 2 rows with different lambda and sigma in 2 states. We can find that the flow assignment results on both two roads are significantly affected by the states of the network. Second, there exists a critical value of lambda that divided the area into 2 parts, which is consistent with the above analysis. Look at the figure 5. Figure 5 shows the flow assignment on the route 1 with different lambda and sigma in 2 states. Figure 6 shows the total social cost with different lambda and sigma in 2 states. From these 2 figures, we can find that the total social cost of the abnormal states is higher than that of the normal states. Second, the area of figures 6a and 6b are divided into 2 parts by the critical value of lambda, corresponding to 2 regimes. Table 1 shows some numeral results with different lambda and sigma in 2 states. SOC means the social optimal cost, and POA is the ratio of IC and SOC. As shown in Table 1, the total social cost of the abnormal state is higher than that of the normal state. And in regime 1, the value of IC decreases with increasing sigma. The total social cost in regime 2 is fixed. The finding of Table 1 is consistent with figure 6. Okay, then let's begin our conclusion. When the network is normal, increasing the TIS user proportion minimize total travel cost at equilibrium. TIS compliance rate significantly impact total cost. 50% is the point. Total costs are lower than without TIS only when compliance rate is higher than 50% in regime 1 or in regime 2. Okay, thank you.
Are there any questions regarding this presentation? So I'm not very familiar with this subject, but can you show the slide 18 when you show the conclusions? Slide 18?
Oh, okay.
Yeah. So the second point here, so total costs are lower than without TIS when compliance rate is higher than 50%. So that means that if people are more compliant to traffic information system, the total costs actually increase. Sorry. Oh, okay. So I misread that. Total costs with TIS are higher for okay. Compliance around 50%. Okay, so then my Halubis has I cannot unmute you, but can you write your question on the text? So what about the actual degrees of compliance? Because I would assume that most people now just ask GPS to take them wherever they want. So I would assume they are very compliant. What do you think about that?
Oh. 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 Look at the left picture. Mm, the flow of float R1 is 0.5 is what you said.
No, I mean, I was referring to the actual compliance rate. I would assume that now because everybody rely on GIS and GPS systems. Wouldn't you agree that in general people just are very compliant?
I think all of people have bias. Someone prefer the roads they often use without TIS.
So you think people do not listen to TIS that much?
Yes.
Okay. Okay, so Halubis has raised. Oh, there you go. Inform or not? Can you see the question in the chat? So any penetration level found because we've all informed the network shortest path change over time. They say 20% penetration level will be max. Do you care to answer for that question?
Oh, wait a minute.
Indesa, can you make him a host so he can unmute himself maybe? I think it's okay at this time.
informed and not informed TIS and penetration level found, because if all it's I can't understand this question. Could you pardon? How come information? It's a good question. That's what I study at present. A good information design will take minimize system costs. That's what I study in these days. That's all.
I guess his point was to some extent that if everybody gets the information, then maybe the network shortest path will change because people trial behavior will also change, right? The route choice will also change.
Change because change. Yes, I think the network state is not sure. Yeah.
Okay. Thank you. So if there are no
thank
other
you.
questions, then I would like to wrap it up here. I think with this we conclude. I think the other session is still running, but we conclude the second day of BTR on the Eastern Hemisphere. Thank you very much for joining, and I look forward to seeing you next year as well. Andresa, thank you for
Thank you so much.
the back office work.
Thank you so much for sharing this session.
Okay, so with that, we'll wrap it up here. Thank you very
Thank you
much.
so much.